Welcome back. Our prior video went through 3 well-known papers that have operationalized this idea of doing partial identification or sensitivity analysis with an OLS regression model to try to reason about how much of a threat unobservable selection is to making a causal inference about a regression coefficient of interest. And I wanted to, in this video, go in depth into a recent paper that generalizes the previous approaches and makes everything a little bit more easy to understand and systematic in its analysis. And the paper I'm talking about is written by Paul Diegert, Matt Masten, and Alex Poirier. And I'm filming this in November 2025, and this paper is hot off the press. It's only been out as a preprint for 4 months. And we'll go through in detail how this paper builds on the prior approaches and some of the implementation details that we should be thinking about as applied researchers. Let's revisit the equation that I put on the slides several videos ago. And one of the main innovations that this paper makes is that it relaxes the assumption that X and W are independent. So in the prior papers, they always assumed that the X's were exogenous, but this is almost as crazy of an assumption as assuming that treatment is exogenous, conditional on X. And it's well known that this is not something that we should ever expect to be true, but the earlier papers had to start somewhere, so I'm not bagging on them. I'm just saying that I really like this approach that we're going to go through in this video. So the main idea is that this Diegert, Masten, and Poirier paper is innovating on the past ones by allowing the controls to also be endogenous, not just the treatment to be endogenous. And if you're reading this paper alongside watching this video, I just want to make it clear that I've made several notational changes relative to the paper in order to stay true to the prior videos and some of the prior work that's been done on this topic. What I call D for treatment, this DMP paper is going to call X. And what I call X, they call W1. What I call W, they call W2. The treatment effect in these slides is going to be denoted by alpha. And they denote it with beta. And then what I call beta and gamma, they call gamma 1, gamma 2. And then what I call nu, which is the error term, they denote it with linear projection notation. And then I keep y lowercase, they capitalize y. So that's basically all of the notational substitutions that I'm making as I present this paper. Hopefully it won't throw you too much for a loop. Let's also establish some terminology before we go further. We're going to talk about a long regression, which is the regression that we would like to run, but that we can't run because we can't see W. So in the long regression, the coefficient on D would be equal to the causal effect. Then we have the medium regression, which is just the regression of Y on D and X. And throughout this, I'm also assuming that we have an intercept in there. The paper is very clear about where intercepts enter and where they don't. That's not a detail that I'm concerned with for the purposes of this video. So the medium regression we can run because we have all the data, but it's not going to give us an alpha hat estimate that represents a true treatment effect. And then we also have a first stage regression, which is a regression of D on X and W. And this is basically a way to conceptualize what we mean by selection on observables or unobservables. And then something that they mention in the paper is a short regression, which is just a regression of Y on D. I didn't put it in these slides. But basically, we can get different estimates of alpha from the long or the medium regression. We can also get an alpha from the short regression, and that can help us reason about what alpha long might look like because it's infeasible for us to estimate it. And when we think about selection on observables versus selection on unobservables, we want to be thinking about this first stage regression. We can write it down generically as D is equal to X times psi plus W times phi plus eta. And what we want to do is think about how X is correlated with D and how that compares with W's correlation with D. And we can think about this ratio as being summarized by a number, which we call R sub D. And we can just think about the standard deviation of the linear index W times phi relative to the standard deviation of the linear index X times psi. And that is basically functioning as the lambda in the Krauth paper from the previous video. And so the intuition here is that R sub d is basically the same as this lambda that we talked about earlier, that the variance of this linear index is sort of like the correlation between d and x beta, and the variance in this linear index w phi is sort of like the correlation between d and w gamma. I know it says d and epsilon here, but hopefully you get the idea. And again, this is just a little more formal, a little more systematic, and that's why I appreciate the additional clarity that is granted by the rigor. So the question is, how do we use this information? In the previous video, when we talked about the Krauth paper, the recommendation was to use R sub d as a sensitivity parameter. If R sub d is 0, then we're basically arguing that all of the phi's are 0. And if we're arguing that R sub d is equal to 1, then we're arguing that these two linear indices are the same. So getting back to the question of how to use this information, the authors suggest that we, as applied researchers, present the breakdown point for our model, which is a value of Rd such that alpha equals 0, because if Rd equals 0, then we just have our medium regression estimate. And they recommend presenting this alongside the other regression statistics that we would normally report, like the sample size and the R squared. And this is a single number that represents how robust our estimate is to selection on unobservables. And then another thing that they recommend doing is to present the identified set of alpha long as a function of this breakdown point. And so we can think of some adjustment delta that is a function of whatever value of Rd we want to assume, and that the alpha long becomes an interval that's symmetric and widens as we take R bar d higher. And the breakdown point is just defined as where does this interval start to begin to contain 0. But we can also just think about what would the interval width be for other values of R bar d. And then obviously if R bar d is 0, then we're just going to get the medium regression estimate back. And then as I said, this set is going to widen as R bar d grows larger, and eventually we could come up with a value of R bar d such that the set would include the entire real number line. And one way that we can present this identified set is by graphing it as a function of R bar d, but there are, of course, other ways to present that as well. And this paper also comes up with sensitivity parameters that we can use to gauge the strength of our analysis and its conclusions. There's R bar d that I already went through, there's R bar y, and there's C bar. R bar d, as we just mentioned, is going to be an upper bound on the relationship between the selection on unobservables and the selection on observables. R bar y is going to measure how much the unobservables can predict the outcome compared to how much the observables can predict the outcome. So it's analogous to R bar d. R bar d concerns itself with the selection equation, and R bar y concerns itself with the outcome equation. And then C bar is going to govern how much we're allowing the x's to be endogenous. If we set C bar equal to 0, then we're imposing that the x's are exogenous, which is what all of the prior literature that we reviewed imposes. And so this C bar and this R bar y are innovations relative to the existing literature. So then you might be thinking, well, what's the actual formula for R bar d? And it turns out it has a closed form, which I think is absolutely stunning. And it's actually quite a simple formula. It's a function of R squareds of various regressions with different ratios and summations, and then with a square root applied. So what are these components? R squared y tilde d dot x means I'm going to partial x out of y and d, and then run a regression of y on d. And then the R squared of d on x is just the first stage regression that we already talked about. So I have this quotient, and then in the denominator there's another quotient, and then I take the square root of everything. And basically this just depends on two features of the observed data, which is what's the medium regression, the relationship between y and d after we adjust for x, and what's the first stage, the relationship between d and x. So in that sense, it's pretty impressive that we can think about these two intuitive objects and come up with a fairly simple formula that describes the breakdown point. And obviously, this is super simple to compute, and so it's going to be very easy for us to impose different constraints into this system and think about, well, how would alpha change if I changed r bar d by a slight amount, and so forth. So in the end, what should researchers report now that you kind of have a handle of what this paper is bringing to the table that's new? Well, first, you should always report the breakdown point. And typically, this is going to be a number between 0 and 100%, and it summarizes the robustness to the omitted variables. We also want to typically plot the identified set as a function of r bar d, like we talked about earlier. And this is going to easily communicate how do my conclusions change as I allow for stronger selection on unobservables. And then another thing that they recommend doing is to calibrate your breakdown point against how sensitive the d is to each of the x's. And they're calling these rho sub k, which is basically a ratio. It's kind of like the ratio of the standard deviation of linear indices that we talked about earlier, but doing it for different subsets of the observables. And we want this r bar d breakdown point to be larger than any of these rho sub k's. If that's not the case, then it's likely that there's another w out there that could undermine our alpha medium. And I'll get into this a little bit more in the next video when we go through a practical example. And then finally, we can also impose that r bar d is equal to r bar y, and then report that resulting breakdown point. There's a trade-off between r bar y and r bar d, which they call the breakdown frontier. And so if we make an assumption about them being equal, then that's going to be a less conservative assumption than what's up here in number 1, but that's going to be another number that we could report that could communicate the robustness of our results. And again, it's less conservative to put this breakdown point that imposes equality between the r bar d and the r bar y. And to give you a sense for how this rho sub k idea works, I wanted to pull up their paper and show you how they do it in one of their empirical examples. So if we go here, they're reproducing an analysis from another paper in Econometrica. And in this Republican presidential vote share column, column 5, they're getting a breakdown point of 80% and a less conservative breakdown point of 95.9. So these look like pretty solid numbers, especially considering, say, column 1 has a breakdown point of 3% and a less conservative breakdown point of 54%. So that's the context. And then if we go down, to this table, we want to keep in mind that the breakdown point here was 80% and the breakdown point here was 3%. And we can see that all but one of the covariates of interest is below that R bar breakdown point for the presidential vote share equation, but that all of them are above the R bar breakdown point for this column 1. So that's kind of the intuition. So the intuition is that, well, if almost all of my X's are not contributing anything above and beyond my breakdown point to the observable index, then I'm unlikely to find any W's that are also going to overturn this. Whereas in column 1, all of my observables are above this breakdown point, and so there's no question that I'm also going to have a bunch of other unobservables that would overrun that breakdown point. So hopefully that was a little bit informative as to what we can conclude from these different quantities that were being suggested to report by the authors of the paper. Lastly, I'll answer 2 questions that I've heard people ask me when I've discussed these methods with them over the years, and actually questions that I've posed to these authors themselves. So one is, can this approach be used in a nonlinear model like a logit or a probit? And the answer to that is no, because identification becomes much more complicated when we get into nonlinear settings. And then another question that is common is, can I use this in a panel data setting? Everything we've talked about in all the videos so far has been cross-sectional. Can this be done in panel setting? My response is, I think so, but you just do everything on the within transformed data set. So the main equation, instead of being y regress y on d and x, you're instead regressing y dot on d dot and x dot, where this dot is a transformation that does the within transformation. That's common if you've ever looked at fixed effects models. And obviously here, the treatment would need to be time varying. And so then that might open up other questions about how to interpret these results and how to apply them. So I'm going to leave this second question to the experts on this topic, but it seems like you could just do the within transformation and then continue on. So that was a lot to chew on, and hopefully you found that worthwhile. In our last video of this mini-series, I'm going to walk through an example of how to apply these tools to a publication of mine, and hopefully that will help you see how these things can be used in practice. So I hope that you've enjoyed this one, and I hope to see you in the next one as well.